Welcome to This Explainer. Today, we're going to uncover the incredible science and the really fascinating real-world applications of something called the Canadian well. It's actually an ancient technology, but it's making a massive, modern comeback in sustainable architecture right now. We're going to break down exactly how it works, how much it costs to build, and why it just might be the absolute future of energy-efficient design.
So let's just dive right into this massive question. In an era where we are constantly battling extreme heat waves and soaring electricity bills, finding passive ways to regulate our indoor environments is absolutely critical. And this single concept we're exploring today, it's completely redefining how we think about heating and cooling our spaces.
Section 1. The Earth's Hidden Battery. To understand how we can actually passively climate control our buildings without relying on power-hungry air conditioners, we first have to look right beneath our feet. It all comes down to thermal inertia. See, while surface temperatures wildly fluctuate from freezing snowy winters to scorching dry summers, the soil just roughly 6 feet, or about 2 meters underground, stays remarkably consistent. It holds steady right around 50 to 60 degrees Fahrenheit, or 10 to 13 degrees Celsius, literally no matter what is happening up above.
So the core physics of the system rely on what is basically nature's perfect heat exchanger. During the summer, pulling hot surface air down into the earth transfers its heat to that cooler soil before it even enters the home. And then conversely, in the winter, the relatively warm soil transfers its heat to the frigid incoming air. It's elegantly simple.
Section 2. How Canadian wells work.
Let's trace the journey of the air, which happens in 4 distinct steps. It all starts with a protected outdoor intake filter. Got to keep out the dust and debris, right? Then, that air travels through precise lengths of buried pipe, where the real magic of conduction and convection happens with the surrounding soil. Finally, this perfectly preconditioned air is tied directly into the building's mechanical ventilation system.
And the temperature spikes and drops here are super significant. I mean, imagine taking punishing 35 degrees Celsius summer air, that's mid-90s Fahrenheit, and passively chilling it down to a comfortable 26 degrees before it ever reaches the house. Or, in the dead of winter, taking 3-degree freezing air and warming it up to 15 degrees Celsius. That is a massive head start for any HVAC system, and it's powered entirely by dirt.
Section 3. DIY Amish Air Conditioning.
Now let's look at a classic high-stakes, real-world situation. An off-grid homeowner in Idaho, completely desperate to escape a brutal, triple-digit summer that was totally overwhelming his solar power grid, turned to an old concept. Some folks actually call it Amish air conditioning, or earth tubes.
Armed with an excavator and a pretty bold mindset of, I'm going to trust the math, do the work, and see what happens, he committed to digging a massive 6-foot trench right through his front yard. His goal? To tap into that stable 60-degree earth temperature he had recorded at the bottom of the dig.
And here is the craziest part, $700. That was his total one-time investment for the underground pipe and fittings. Just $700. That is a stark contrast to the $10,000 to $12,000 a traditional air conditioning unit would cost for a typical 2,000 square foot house. And again, that is a one-time upfront cost for the piping. So how did he do it? Well, by doubling up 240-foot runs to create 280 total feet of pipe, he ensured he had enough surface area for the heat exchange. He used thick 125 psi irrigation pipe with push-fit rubber seals to keep the dirt out. And he meticulously added drainage holes wrapped in aluminum screen right at the lowest points to deal with condensation. He basically built a localized, highly functional heat exchanger right there in his yard.
Section 4. Scaling up to commercial giants.
So you might be wondering, how do we scale this up for larger buildings? While our DIYer used a direct air system, which is pretty common in residential builds and even some larger spaces like the Cambridge Public Library, massive multi-unit public buildings often go a different route. They use fluid-based systems. These pump a glycol water mixture in a closed underground loop. The fluid gathers the temperature from the soil, then exchanges it with the building's air through a heat exchanger. This entirely separates the soil from the breathing air, completely preventing any humidity or bacterial risks.
And the results are incredible. At the National Renewable Energy Laboratory in Colorado, they have a LEED Platinum office building that proves this passive strategy works on a massive scale. It contributes to a jaw-dropping 56% lower total energy use compared to standard buildings in the exact same climate.
To pull off that kind of efficiency, the NRL facility uses exactly 42 buried earth-to-air tubes. Just think about the sheer volume of air moving through there. They use this whole labyrinth of tubes to precondition 100% of their outdoor air before it even touches their mechanical ventilation systems.
And backing up the American data, there was a rigorous field study over in France by ADEM. They proved the system can operate with a COP, or coefficient of performance, of around 12. In really simple terms, for every 1 unit of electrical energy spent running the fans to move the air, you get 12 units of thermal energy back. That yields a massive 40% reduction in mechanical heating demands during the winter.
Section 5. Weighing the pros and cons.
Now, it's not all sunshine and perfect temperatures. The absolute biggest enemy of the Canadian well is poor design. Physics dictates that when warm air hits cool pipes, condensation happens. If you don't calculate the correct downward pipe slope for condensate drainage, or say you fail to clean the intake filters, water droplets just pool up. Your brilliant energy-saving system can very quickly turn into a moldy, incredibly expensive underground swap.
But when it's done right, sustainable architects are completely obsessed with it. It's a 100% refrigerant-free solution with a 30 to 50 years service life. It perfectly aligns with bioclimatic, low-energy building design, meaning it dramatically reduces a building's carbon footprint while maximizing human comfort.
However, what you really should take away from this is that it is not a magic bullet. We can't ignore the high initial earth-moving costs and the super strict engineering required to pull it off. It's also highly dependent on your local soil. Moist clay, for example, conducts heat way better than dry sand. And finally, you just simply need a lot of physical land to bury hundreds of feet of pipe, making it pretty tough for dense urban areas.
So, I want to leave you with this provocative thought to ponder long after this explainer is over. We have this massive, completely free thermal buffer right beneath our feet. As climate change pushes extreme temperatures higher and higher, is the Canadian well, despite its space and engineering requirements, the ultimate key to resilient architecture in our rapidly warming world? Thank you so much for joining me to explore the science and the incredible potential of this underground technology. See you next time.